Hi, Miss Redican here, and we're going to be taking a look at nuclear chemistry. It might seem a little intimidating, but we're going to just learn the basics, and you're going to see it takes a lot of review into account, so it's going to be a great thing. Here we go. So let's start with a review of the atom. Out here, we've had these electrons and these orbitals, these energy levels. Right, so we've been talking a lot about electrons for most of the last few months. The nucleus hasn't been changing. We've been talking about all kinds of chemical reactions, physical changes, and the nucleus stays uninvolved. The nucleus full of protons and neutrons. The positive nucleus, because the only thing inside the nucleus with a charge is the positive proton. Neutrons are neutral. So we have a positive, small, dense nucleus, and the electrons, which do most of the work, so to speak, in chemical reactions. But we're going to take a look and focus a little bit more on the nucleus as we wrap up the year. You might remember isotopes. Isotopes are atoms of the same element. They have the same number of protons, same atomic number, but different neutrons, different mass. Let's take a look. Atomic number is always here on the bottom left, and the mass number up top. Remember, mass number is the protons plus the neutrons. Basically, it's the mass of the nucleus. Let's try a problem. Which of the following pairs are isotopes of the same element? So the letter X just means unknown. There's no element X. So you really need to look for isotopes. Isotopes have the same atomic number and different masses. Take a second, see if you can find it. Okay, hopefully you found B. Same atomic number, different masses. That would make these isotopes. So, turns out most isotopes are stable, but some are not. And that's what we're going to learn about in nuclear chemistry. The unstable isotopes. Here we go. So these radioisotopes, or radioactive isotopes, first started being studied about 150 years ago. And one of the major scientists involved in this study was Marie Curie. So we're going to take a look at a clip from this film about her life.
We thought we would find a new element. We were wrong. It's taken 4 years, 4 tons of pitch blende, 40 tons of corrosive chemicals, and 400 tons of water. We are here to present to you 2 new elements, polonium and radium.
We all thought that atoms were finite and stable. Well, it turns out some of them are not. And in their instability, they emit rays. I have called this radioactivity. We are here to tell you that you have fundamentally misunderstood the atom.
We thought we would find a new...
There we go. So let's take a look at what makes something stable or not stable. And it turns out it has to do with the protons and the neutrons and the comparison of the two. The more protons you have, the more neutrons you need to keep it stable. So you can see here, as things get larger, the number of protons increases, you need even more extra neutrons to keep it stable. Radioisotopes have an imbalanced proton-neutron ratio, and that's what's going to make them unstable. So, natural radioactivity occurs all the time around us, and for the most part, it's benign. It's not a problem. Now, in different quantities or in different dosages or different intensities, it can be very much a health issue. Okay. When does it occur? Well, it occurs when nuclei are unstable. So we're not going to talk about electrons for a while now, really. It's really going to be more about the nucleus. And if it's unstable, we call it a radioisotope. So let's take a little look at, we have a scene here from Radium Girls. Some of you might know that play, and it's also been turned into a movie. And why we study radioisotopes. We know they're unstable. Let's see.
In the 1920s, women were often hired to perform tasks deemed too delicate or menial for men. That's how Wendy got hired onto an all-female work crew at Radium Corporation, a New Jersey company that made military watches and clocks. Wendy and her co-workers were given the job of painting the numerals on the watch faces. They used a new kind of paint called Undark.
The glow-in-the-dark fluid that they were using to paint the faces of the watch, the reason that it glows is because it's radioactive, and it's a compound called radium. What causes problems for this woman was that she probably ingested it.
This kind of detailed work was exacting. To keep the tip of their paintbrushes pointed, the ladies were taught to wipe excess paint off on their lips. The Radium girls discovered Undark had a hidden benefit.
Lips making trips.
They could apply it to each other and literally make themselves radiate.
Once it's in the body, it mimics calcium, and so your body incorporates it into bone. And so a lot of these women ended up getting bone cancer. It was damage anywhere that it came in contact. If they were ingesting it, it would cause damage in the stomach and the intestines, the throat, the tongue, mouth.
Wendy thought it would be fun to use her new look to light up her sex life.
Uh-huh. Isn't it kind of sexy?
Why don't you get over here, you little glowworm?
Numerous times, Wendy and her husband played peekaboo with the magic paint. But before long, they realized that something about this cutting-edge technology was making Wendy bleed in the most bizarre places.
Radiation causes DNA damage, it'll cause mutations, and that's why when the radium is incorporated into bone, it has a long time to sit there and damage the soft tissue layer inside the bone, and that can lead to cancer, to bone cancer.
It turns out the company knew all along about the harmful effects of radium, yet they allowed the girls to ingest it daily. Wendy was one of the first to die, but 6 of her colleagues banded together in the first successful workers' rights lawsuit. Overcoming years of denial and foul play, the Radium Girls led to higher safety standards across America.
Okay, so we do study radioactivity, and we're learning more about it all the time because it has an impact on our lives, really, for good, and there's some also bad and good uses for it. Again, radioisotopes, that's what we're going to focus on. There we go. So, table N in your reference table is a list of some common radioisotopes. It's not a comprehensive list. But these are the main ones that we're going to be taking a look at. You can see on this table, it tells you the half-life, the decay mode. We're going to learn more about that. That's what it's emitting when it transmutes, okay, and its name. Okay. So when a nucleus decays, it emits particles, like Marie Curie said. And there are certain particles we've discovered they can emit. An alpha particle, which is the most massive with 4 atomic mass units, a +2 charge, and it looks like basically a helium nucleus. This is the symbol, the alpha symbol, and it has very low penetrating power. It's basically fairly weak. Beta, which has no mass and a -1 charge, so it's kind of like an electron. A positron, which is sort of the opposite of a beta. It has no mass, and a +1 charge. And then gamma, the most harmful, the strongest, has no mass, no charge, and has a very high energy. Okay. So alpha decay happens when the nucleus emits an alpha particle. It's fairly easy. Beta decay is when the nucleus emits a beta particle. And positron decay is when it emits a positron. Okay. So let's take a look at some of the particles, the alpha, beta, and gamma. Alpha being the weakest, then beta, then gamma. Look at the diagram and see which particle will travel through the aluminum but be stopped by lead. Okay. Hopefully you said the beta particle. Sorry, the gamma particle, my bad. Okay. So gamma can travel through paper, travel through a lot of metals, but not lead. Gamma is the most harmful. Alpha will be stopped by paper, beta by your typical metals like aluminum, but gamma will go through most things except lead, which is why when you go to take an x-ray, like at the dentist's office, they'll put a lead vest over the core of where most of your major organs are to protect that, and then they'll take the x-ray of your mouth. Okay? So that vest that's so heavy has a lead in it to protect you from some of that gamma rays. So there's different kinds of radiation or radioactive reactions. Natural transmutation is one. You can see it here. It begins spontaneously. So let's take a look. You can always tell natural transmutations because there's one reactant. So notice, let's take a look at the GIF. It starts off as fluorine and naturally is losing. Right? Just naturally, spontaneously losing. That's a natural transmutation. One reactant naturally breaking down. We also have artificial transmutation, where humans, we can manipulate this and bombard the nucleus with something. So in artificial transmutation, you're going to have an element and a particle. This is an alpha particle. Remember, alpha particle is like a helium nucleus. You can tell artificial transmutation because it has two reactants, an element and a particle. Okay, fission is often used in nuclear power, also nuclear weapons. And you have usually uranium, it could be plutonium, but usually uranium and a nucleus coming together, and it splits. So let's take a look at the picture here. You have the nucleus, or neutron, hitting the nucleus of the uranium and splitting it and creating more neutrons. So again, really splitting it in half almost. Okay, again, fission starts off with a neutron hitting that uranium nucleus, and it creates even more neutrons, which will then hit other nuclei, creating this chain reaction and creating a lot of energy. Okay, it's used in nuclear bombs or nuclear meltdown. Also, it can be controlled to make nuclear energy. Now, fusion sounds similar, but is the opposite. Fusion means to come together. Fusion happens in stars like our sun. And you have very light elements, almost always hydrogens, coming together to make something like helium. Right? So you can see if they're fusing together, a lot of energy is released. Right? The sun gives off a lot of energy as this fusion is occurring. Again, the combining of small nuclei, again, almost usually hydrogens, to produce slightly heavier ones like helium. So fission and fusion, they sound very similar. Okay. So nuclear reactions give off a lot more energy than a normal chemical reaction. And fission gives off more energy than fusion. Okay. Fission and fusion reactions appears to be a loss of mass. However, this mass is converted into energy. And Einstein here came up with that equation, E, energy, equals mc squared. Mass times the speed of light squared. So a small amount of mass really gets multiplied greatly and creates a lot of energy, nuclear energy. Okay, tomorrow we're going to be starting nuclear equations, and we'll learn how to do some simple math to understand what's happening at that atomic level. Okay, but that's it for now.